practice exam problem 6. We need to find the electric field and the potential everywhere for a spherically symmetric charge distribution, where the charge is more charged in the center, less charged off on the edge, and so it becomes more tenuous as you move out for edge. It dies off linearly, and then at capital R it goes to 0 and just stays 0 after that. And so the idea is to find the electric field and the potential everywhere for that system. We've got a symmetric system here. The clear way to do this is to draw a Gaussian surface. Okay, it's to use Gauss's law to find the electric field. And so we draw a Gaussian surface somewhere in our charge distribution, and then we start out with Gauss's law. So Gauss's law always states that the integral, closed integral over a surface, d2x n hat dot e, should equal the volume integral d3x rho by epsilon naught. And so this is a integral statement of Gauss's law, and we're just going to apply that to our system. Now, symmetry-wise, right, our n hat is always going to be in the r direction, and furthermore, by symmetry, right, we know that this e vector is going to be a function. It's only going to point in the radial direction, and it's only going to depend on the radial variable. It's not going to depend on theta or phi at all. And so by symmetry we can make the following argument, and that's just the definition of n hat if we have a sphere. What does that mean for us? That means n hat dot e is going to be a constant e of r on the surface. Okay, so the left-hand side of this takes our standard form, 4 pi little r squared if little r, okay, is the radius to our Gaussian surface. 4 pi little r squared, that's this term, that's the integral over the surface area. This is a constant. This is just e, the function of r, should be equal to the charge enclosed. And so this is where we have to actually do the integral. And so this is going to be equal to using spherical coordinates, right? This is 1 over epsilon naught times the integral 4 pi times the integral r squared dr from 0 to little r. So I'll make those primes of a rho of r, like that. Okay, r prime. Okay, so that is what we need to do to find the electric field. We need to evaluate the right-hand side of this. A little bit of simplification happens straight up, right? Is we are going to have the 4 pi's on both sides cancel, and we could divide both sides by little r squared if we want. And so that's going to give us the electric field, the radial component of the electric field is 1 over epsilon naught, 1 over little r squared, and the integral from 0 to little r prime squared dr prime times rho of r prime. And so that's what we need to do to evaluate the electric field. And so let's just evaluate that then. So for little r less than capital R, this guy has a closed form, then dr r squared 1 minus rho naught, 1 minus little r over capital R prime from 0 to little r. This is easy because this is just integrating power. So there's an r squared, or there's an r cubed when you do r squared times the r there. So the integral of r squared is 1/3 r cubed, and so this will be rho naught times r cubed over 3 minus r to the 4th over 4 capital R. So that's that's that. For little r greater than capital R, then the integral cuts off at capital R. So we do the same thing, but now we plug in capital R. So this will be rho naught of capital R cubed over 3 minus capital R to the 4th over 4 capital R. This simplifies, right, to rho naught capital R cubed over 12. And so now we can write E of R is going to be, so we have to break this into two regions. This will be rho naught over epsilon naught, so 1 over epsilon naught. We still have the 1 over little r squared, and so distributing that in there, so there's the epsilon naught, the run over little r squared, is going to give us r over 3 minus r squared over 4 capital R hat for little r greater than r, and it will give us rho naught over 12 epsilon naught capital R cubed over little r squared r hat for little r greater than capital R. And so that is the electric field everywhere for that charge distribution. And if we wanted to plot it, so let's do a quick plot. Make this capital R. Then we are going to have an expression that goes as 1 over little r squared out here, and then it's quadratic here. So we have something parabola-like. Parabola. Okay. So this is the plot of the radial component of the electric field versus little r. Next, we need to find the potential, the electric potential, as a function of little r. The electric potential, by definition, V of r, by definition, minus the integral dl dot the electric field. And so now that we have the electric field, we can integrate the electric field from infinity to give us that. And so again, we're going to do this for two different regions, but now our region is going to be, we're going to do the r greater than capital R first. And so for little r greater than capital R, then V of r is going to equal, let's see, minus the integral, dl is just going to be dr, or dl dot e is going to be dr, and then the radial component. And so this will be rho naught for 12 epsilon naught capital R cubed from infinity to little r, so we'll put primes on the little r. There we go. The integral of 1 over r squared, right, is just 1 over r, and so that's pretty easy. And so this is going to give rho naught over 12 epsilon naught capital R cubed over little r, and the other one goes to 0 because off at infinity it's 0. For r less than capital R, we've got to do something a little more subtle. Right? So V of r is going to be equal minus from infinity to capital R dr prime, same thing we have here. And then we have to also go from r to little r of the function in that region. And so over Again, the integral is easy to do because we have just it's just powers, and so we can carry that out. This one we've already done, so this is rho naught over 12 epsilon naught, capital R cubed over, now we have to evaluate it over little r, like that, and so that simplifies obviously. And then plus, now we have to evaluate these at the endpoints. So rho naught over epsilon naught, evaluated at the endpoints, and so we're going to get capital R squared over 6. That's the 1/2 r squared times the third there, minus capital R cubed over 12 little r. So that's the one endpoint, and then the other endpoint is going to be minus little r squared over 6 minus little r cubed over 12 capital R. A little bit of simplification. B of r in this region. This simplifies. This right here simplifies, right? To r squared over 12. So r squared over 12 plus r squared over 12 is going to give us rho naught r squared over 6 epsilon naught minus rho naught over 6 epsilon naught little r squared plus rho naught over 12 epsilon naught little r cubed capital R. And so now, just summarizing and putting it all in one spot so we can look at things easily, we are going to have the potential V of R is going to be, so it is rho naught over 12 epsilon naught R cubed over R for R greater than capital R, and then it is rho naught over 6 epsilon naught, that factors out, r squared minus little r squared plus 1/2 little r cubed over r for r less than capital R. And if I were to plot this, then this is going to have the form that out here. It has the form 1 over r, and in here it's cubic. See, it has an r cubed in it, it's cubic. And so that is a sketch of the plot in that region. There you go, that's how to do that.